Today, we are going to be going through group theory. If you take one thing away from this video, I want you to take away the fact that Cyfrin is incredibly awesome. I would urge you to stick around to the end of this video to understand why I am telling you that Cyfrin is incredibly awesome. Okay, so first of all, why am I teaching you group theory? Why did I teach you about modular arithmetic? Why did I teach you about set theory? Which, by the way, are the prerequisite videos that I have already posted. They're going to be linked below this video if you would like to catch up. Group theory sounds a little bit intimidating due to the fact that it has the word theory in it. It sounds a bit fancy, and to be honest, it's really not that fancy. It's what we call an object in maths. It's a mathematical construct in order to describe things. For instance, we can describe a collection of numbers as a set. A group is just another way to describe things. If something is a group, then we know that it has certain properties. And you need to understand this language to read and understand complex mathematical concepts such as cryptography and zero-knowledge proofs. And you need to be pretty familiar with it so that you can read it in context, like group, and understand, I know exactly what that means. What actually is a group? Now, I'm going to write this out for you, but you will not know what this sentence means from the first time that I write it / say it. A group is a set, I remember we've learned about this word set before, of elements. So if you do not know what these words mean, then I encourage you to go watch the video on set theory linked below, equipped with a binary operator that satisfies the following properties. Number 1, closure. Number 2, it has an identity element. Number 3, every element has an inverse. Number 4, associativity. These are the 4 things that the set of elements needs to satisfy when equipped with a binary operator. Now, as I said, you will not understand, or I mean, you might, but do not worry if you don't understand what this means, because I'm going to go through it all now, one by one. And let's start with the phrase binary operator. What the frick is a binary operator? This term sounds scary, but it really, really isn't. So let's quickly define it. So a binary operator is a type of, this needs an O at the start, operator that takes 2 operands to perform an operation. Operator, operand, operation. So typically we denote the binary operator with a dot. It can also be other symbols like this one, or like a star, and lots of others, because it depends. Sometimes we use the star to denote multiplication, sometimes we use the dot to denote multiplication, sometimes this means point addition. It varies, but often we do use the dot just to mean any arbitrary binary operator. We can show mathematically this definition by saying that the binary operator dot, or C dot if you're in latex, but central dot, is operating on the 2 operands A and B. So if we label this, we can say that this is the binary operator, and A and B are the operands. Now, just to make this clearer, I'm going to remove these symbols up here. I'm actually going to make these arrows black just to make it a little teensy bit clearer. So these guys are the operands, the things being operated on, and this is the binary operator. The instructions for the calculation. You have some kind of instruction that takes 2 operands, which are like 2 elements from a set, 2 numbers. The operands are the things which the operator is operating on, and some calculation is performed on them using some instruction, which is the operator. And by binary, it means we take 2 of those operands to perform the operation. Let's go through some binary operator examples to make this a little bit clearer. So binary operator examples. Maybe pause the video and see if you can think of any. Well done if you have, because it means that my explanation a second ago was clear enough. But we have lots of different types. So we can have arithmetic operators, and this includes addition. For example, 3 plus 4. And here you'll see we've got the binary operator, and here we have the operands. We have subtraction, multiplication, division, and the one that we've learned in a previous video, the modulus operator. For instance, 10 mod 3. We can see here we've got the binary operator and the operands. Now that we've done some examples, see if you can think of any more examples before I continue. Let's do a couple more examples. So we can also have comparison operators, to be more specific. And these are things like equal to, which is usually denoted with equals equals, not equal to, which is the equals with a slash through, greater than, for example, 4 is greater than 3, less than, for example, 3 is less than 4, greater than or equal to, for example, 4 is greater than or equal to 4, and 4 is greater than or equal to 3, and greater than or less than. And we use the underline underneath the greater than symbol to mean or equal to, or less than or equal to. Let's go through another type of binary operator, and this is Boolean operators. Oops, I spelled that wrong. Boolean operators. For instance, and, or, XOR, not. Now, typically, we are going to be using these arithmetic binary operators, such as mainly addition and multiplication, but we are also going to define some new ones when we talk about elliptic curves, but don't worry about that right now. So now that we know what binary operator is, for example, the expression 3 plus 4, the plus operator is the binary operator that takes the two operands 3 and 4 and performs the calculation of addition. Now that we know what a binary operator is, we can go back to this definition of a group. So remember, a group is a set of elements equipped with a binary operator. Now we know what binary operator is, that satisfies the following properties: closure, identity, inverse, and associativity. Let's go through each of these now. So number 1, closure. Closure is a mathematical term, and what we mean is that the operation must be closed. So the operator that the group is equipped with, such as addition, subtraction, multiplication, XOR, and modulus, must be closed. Now, you still don't know what closed means. When the operator is applied to any two elements in the set, the result is also an element in the set. So let's take two elements from the set, A and B, and we apply the binary operator. And remember, this just denotes any binary operator. And for this operation to be closed, this must equal another element in the set. So A, let's actually move this down. A, B, and C must all be in the set. Again, as always, this is best explained with an example. Let's take the set of integers. Specifically, let's take 3 and 4. So here, A equals 3, B equals 4. And we're going to use the addition operator. So we've got the set of integers equipped with the addition operator. If we do 3 plus 4, that equals to 7. Is 7 in the set of integers? Yes. So therefore, the set of integers equipped with the addition operator does have closure. So closure is, to summarize, when the operator is applied to any, so every single element in the set this must apply to, two elements in the set. I haven't got enough room. Let's move this down again. The result must also be an element in the set. Okay, so now we know what closure means. Let's scroll back up. Now we've got identity. What does this mean? So number 2, identity. Specifically, we mean there must exist an identity element. An element in the set, which is the identity element. So we can write that out. There must exist an identity element, which we usually denote with capital I, in the set. Now, what does identity element mean? It's such that for every element A in the set, every single one, the following property must hold. So A operated on with the identity element must equal to the identity element operated on with A, so the order doesn't matter, must equal to A. So if you operate on the element with the identity element, or the identity element operated on with A, must result in A itself. So as always, let's explain this with an example. So if we take, again, integers under addition, so the set of elements is integers, the operator is addition, then the identity element is 0. So identity element I equals 0. Let's check this. So any element A plus 0 equals to 0 plus element also equals to the element. So for instance, let's say that A equals to 5. So 5 plus 0 equals 5 equals 0 plus 5, which equals to 5. Let's do another example. Let's take the integers under multiplication. Now, I encourage you to pause this video and think of what the element could possibly be, which when applied to any integer with multiplication will yield that element itself. So the answer for this is, of course, number 1. So I equals 1, because any element multiplied with 1 is equal to 1 multiplied by any element, which returns the element itself. And let's again say that A equals 5. 5 times 1 is equal to 1 times 5, which is equal to 5. Additionally, probably addition is not the right word here, so the identity element must be unique. The identity element I must be unique. And this means that there can only be one identity element for that set. There cannot be more than one identity element in any set. There cannot be more than one identity element in the set. Just move that underline. Now, don't worry, we're going to recap this at the end. Let's move on to the third property, inverse. So number 3, inverse means that every element in the set must have an inverse. So what do I mean by inverse? For each element A, any element in the set, there must exist an element, which I'm going to denote A with a subscript inv for inverse, such that when A is operated on with A inv, we get the same as if A inv is operated on with A, and we get back the identity element. So again, let's use an example. And as always, we are going to use the integers under addition. So for this group, the set is integers and the operator is addition. Now, for integers under addition, the inverse element is the negative of that element. So A plus minus A is equal to minus A plus A, which is equal to the identity element, which was 0. So if A equals to 5, 5 plus minus 5 is equal to minus 5 plus 5, which is equal to 0. Now, if we look at this example, and then we restrict this set to be the positive integers under addition, you'll notice that there is not an inverse for every element. There's not an element when operated on, when added to 5, which is positive, which will yield back 0, because we need minus 5 here. But that's not in the set because we've restricted the set to be the positive integers. Therefore, positive integers under addition are not a group. So these do not have an inverse. Therefore, the set of positive integers under addition, not a group, because they do not satisfy the property that every element must have an inverse. Let's do another example. Let's take set of integers under multiplication. So for multiplication, it would be A times 1 over that element is equal to 1 over that element multiplied by A, which equals to 1. Let's say that A equals to 5. 5 times 1 over 5 is equal to 1 over 5 times 5 is equal to 1. Because this would be like 5 over 5, which is equal to 1, of course. Let's move on to the fourth and final property, associativity. Associativity means the way in which the elements of the group are grouped together during an operation does not affect the outcome of that operation. So we can write a little bit about this. Associativity ensures that the result of applying the operation does not depend on how the elements are parenthesized. And this is actually a little bit easier to understand mathematically. So we can say if we take 3 elements, A, B, and C, and these are 3 elements in the set that we are analyzing to work out if it's a group. And if we apply the operator between A and B, and then we apply the result of that with C, this should be equal to, if we take B and apply the binary operator on it with C, take A and then apply the binary operator between A and the result of B operated on with C, these two should be equal. Now let's take an example. And as always, let's take the set of integers under addition. We can say A plus B, then added with C, is equal to B plus C, and then A added with the result of that. If we take A equals 2, B equals 4, C equals 6, 2 plus 4 plus 6 equals 2 plus 4 plus 6, 2 plus 4 is 6 plus 6 equals 2 plus 10. And we can see that 12 is in fact equal to 12, and the integers under addition do have associativity. And now you can do the same thing for multiplication to prove that the multiplication operation for integers is also associative. To summarize, if we take a set of elements and equip them with a binary operator, and then those elements with that binary operator satisfy closure, and remember that closure means that if you apply the operator to any 2 elements, then you get another element in the set. There also must be an identity element, so any element operated on with the identity element must yield the element itself. Every element must have an inverse, so any element operated on with its inverse will yield the identity element again. And associativity. Associativity ensures that the result of applying the operation does not depend on how the elements are parenthesized. And so you can see that the definition of a group really isn't that complicated. You have a set of elements, you have a binary operator, and it must satisfy these 4 properties. And now circling back to the start of the video, Cyfrin is incredibly awesome is the only thing you need to remember, because to work out if a certain set plus a binary operator is a group, you need to figure out whether it satisfies closure, which is C for Cyfrin, identity, which is I for is, an inverse, which is again I for Incredibly, and associativity, which is A for awesome. So here we've got Cyfrin is incredibly awesome. And one of the auditors here at Cyfrin actually does use this acronym to remember what a group is when he is auditing ZK protocols. So now you know what a group is. Amazing. In the next video, we are going to be looking at modular arithmetic. So finding the inverse and identity elements for addition and multiplication, but in modular arithmetic. So analyzing those finite sets, integers modulo some other integer. And to do that, we are going to be having to learn a theorem, which is Fermat's little theorem. So get excited for that, because that is coming very, very soon. And I would love you to comment down below at the bottom of this video that Cyfrin is incredibly awesome, so that I know that you have watched this whole video and that you've enjoyed it. And I'll see you then. Goodbye.